In this lesson, we are going to learn Poisson distribution, and this is the last video on discrete distributions. In the next video, we'll cover continuous distributions. So the notation is x follows Poisson lambda, where x models arrival pattern. For example, number of trucks arriving per day, and lambda is the average rate or constant rate, and the unit of lambda and x should be same. Okay, if it is not same, we'll make it same while doing the calculation. All right, so average rate, for example, average claims per year, so you can see here the unit is year and here the unit is day, so we need to make this same while doing the solutions. Okay, now let's look at how we can derive the PDF. We know the expansion of e to the power x is 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. If I put x equals to lambda, then this is e to the power lambda 1 plus lambda square by 2 factorial, lambda cube by 3 factorial and so on. Okay, and here lambda is greater than 0. Okay, so this is given. Now we can write these terms in summation. This is summation lambda to the power x divided by x factorial, where x goes from 0 to infinity. Now let's bring e to the power lambda to the right side. So this becomes summation x equals to 0 to infinity lambda to the power x factorial e to the power minus lambda equals to 1. Now if you remember the conditions of valid PDF, then the sum of the values of function should be positive. Okay, so here the given lambda is positive. Okay, so this is given, so this term is positive and x ranges from 0 to infinity, which is positive, and exponential is positive. Okay, so its value of this function is positive. Now the sum of values of function should be 1 to satisfy the PDF, which you can see here, this is 1. Okay, so we can say the PDF or the probability of Poisson is lambda to the power x factorial e to the power minus lambda, where lambda is greater than 0 and x ranges from 0 to infinity. All right, now let's look at mean and variance. So mean is lambda and variance is also lambda, so you can say these two are numerically equal. You cannot equate mean and variance because these two are not equal. These are only numerically equal, their units are different. Okay, so these are not the same. Now let's see how we can derive mean and variance. So the expectation of x, we'll use the basic idea of expectation, that is summation x times probability, where x ranges from 0 to infinity, summation x times e to the power minus lambda times lambda to the power x factorial. Now let's expand this term. So this is lambda e to the power minus lambda plus 2 lambda square 2 factorial e to the power minus lambda plus 3 lambda cube 3 factorial e to the power minus lambda plus 4 lambda to the power 4 factorial e to the power minus lambda and so on. Okay, so the first term will remain as it is, lambda e to the power minus lambda. In the second term we can cancel 2, so this is lambda square e to the power minus lambda. In the third term we can cancel 3, this is lambda cube e to the power minus lambda upon 2 factorial. In this term you can cancel 4, so this is 3 factorial, and so on. Now we can take lambda e to the power minus lambda common. This is 1 plus lambda square, this is 2 factorial, lambda cube 3 factorial, and so on. So this is simply e to the power lambda. So lambda e to the power minus lambda times e to the power lambda, this becomes 1, so this is lambda. So expectation is lambda. This is how we can derive the expectation of Poisson. Now let's see how we can get variance. Now for variance we need to calculate the expectation of x square, but there lies a slightly easier way to work out the variance. Instead of calculating x square, we can calculate expectation of x times x minus 1. This is nothing but expectation of x square minus expectation of x. So suppose you find the value of this term, this is say a, then expectation of x square minus, we know this value, this is lambda, so the expectation of x square is lambda plus a, right? So let's find out the value of this thing. Expectation of x times x minus 1. Again we'll use the basic idea, that is whatever is inside the bracket, this times probability. So x minus 1 times probability. X ranges from 0 to infinity. Now let's expand this term. So after expansion we'll get 2 times 1 lambda square by 2 e to the power minus lambda, 3 times 2 lambda cube by 3 factorial e to the power minus lambda, plus 4 times 3 lambda to the power 4 factorial e to the power minus lambda, and so on. Now we can cancel these terms. Okay, 3 factorial gets cancelled, will remain with 2 factorial. Okay, and let's take this term as common. So lambda square e to the power minus lambda, remaining terms are 1 plus lambda square by 2 factorial, and so on. So this becomes lambda square e to the power minus lambda, this is nothing but e to the power lambda. So this is lambda square. Now x minus 1 is lambda square, and this is nothing but expectation of x square minus lambda. So we can say expectation of x square is lambda square plus lambda. All right. So now variance is expectation of x square minus whole square of expectation. So this is lambda square plus lambda minus lambda square. These two get cancelled, we remained with lambda. All right. So this is how we can derive the variance of Poisson. Now let's do one example. If goals are scored randomly in a game of football match at a constant rate of 3 per match, so this is lambda, calculate the probability that more than 5 goals are scored in a match. So this is talking about the kind of events that occurs in a specified time interval, and the events are independent. So you can also remember this, Poisson distribution models the events, number of events that occur in a specified time intervals, and these events are independent. Okay, so now this is very simple. The number of goals in a match can be modeled as a Poisson distribution with mean lambda equals to 3, and then probability of x is greater than 5. So we can write this probability 1 minus probability x is less than or equal to 5. Okay, now we need to calculate for each value of x. So the x ranges from 0 to 5. Okay, there could be 1 goal, 0 goal, 2 goal, up to 5 goal. So we need to calculate this separately. So probability x equals to 0 is, we know the formula, probability x equals to x. This is e to the power lambda, lambda to the power x upon x factorial. So e to the power minus 3, and this is 3 to the power 0, 0 factorial. So this is nothing but e to the power minus 3, okay, which is 0.0498. Similarly, you can calculate for x equals to 1. This is e to the power minus 3, 3 to the power 1, and 1 factorial, okay. And then you can calculate for 2, 3, 4, 5, okay. So I'll leave this for you. I think you can do it. Now let's look at one more concept, Poisson approximation. So the Poisson distribution provides a very good approximation to binomial distribution when n is large and p is small. Okay, typical applications have n equals to 100 or more and p equals to 0.05 or less. Okay, now the approximation depends on the product np, and this is lambda. Okay, so please remember this. The individual values of n and p are irrelevant. You always look at the product np. Now let's look at one example. If each of the 55 million people in the UK independently has the probability this much of being killed by falling meteorite in a given year, use an approximation to calculate the probability of exactly 2 such deaths occurring in a given year. So if x is the number of people killed by a meteorite in a given year, so x is the number of people killed by a meteorite in a given year, then x has the binomial distribution, right, where n is 55 million. We can write this 55 times 10 to the power 6, and the probability of dying is 10 to the power minus 8. Now we can approximate this by using the Poisson distribution, where lambda is np, so 55 times 10 to the power 6 times 10 to the power minus 8, which is 55 times 10 to the power minus 2. We can write this as 0.55. So now probability x equals to 2, okay, exactly 2 such deaths, right, in a given year. So x equals to 2 is 0.55 square divided by 2 factorial a to the power minus 0.55, and this is 0.0873. All right, so this is how you can use approximation, Poisson approximation. Now let's look at another example. The number of home insurance claims a company receives in a month is distributed as Poisson random variable with mean 2. Calculate the probability that company receives exactly 30 claims in a year. Okay, treat all months as if they are of equal length. Okay, so I told you the interval should be equal, okay, and the events should be independent. So now let's define x. X is the number of insurance claims, home insurance claims in a year. Okay, so we are defining this in a year, and we are given poisson lambda 2. So if we write x follows poisson, then we need to change this 2 because this is month. So this becomes 24, right? 12 times 2, 24 for year. Okay, so now the required probability is probability x equals to 30 for exactly 30 claims. This is 24 to the power 30 factorial times e to the power minus 24, which is 0.0363. All right, so this is how you can solve the equations of Poisson distribution. Now let's stop here, and in the next video we'll cover continuous distributions. So thank you so much for watching this video.